You think you know which way is down. You have known it since before you could walk, that insistent pull toward the earth, that direction so fundamental it requires no explanation. Down is down. It simply is. You feel it in your bones, in the weight of your limbs, in every object that falls from your hand. The ground is below. The sky is above. This is not belief. This is the most basic fact of existence. You are wrong, not partially wrong, not wrong in some subtle philosophical sense that makes no practical difference. You are fundamentally deceived about the very architecture of space itself. The direction you call down is not a property of the universe. It is not written into the fabric of reality. It is an accident, a local circumstance as parochial as the view from your window, mistaken for a cosmic truth. Let me show you. Stand where you are and feel the pressure of the ground against your feet. You interpret this as the earth holding you up against gravity's pull. But now consider, a person standing on the opposite side of the globe feels precisely the same sensation. Their down points in exactly the opposite direction from yours. If you could somehow stand back to back with them, feet touching at the earth's center, you would each insist the other was upside down. Who is correct? Neither. Both of you point toward Earth's center and nowhere else. Your down is not the universe's down. It is merely the direction toward the nearest concentration of mass. This is the first crack in your certainty. Now transport yourself in imagination to the void between stars. You float in darkness, 1,000 leagues from any massive body. Which way is down? Point to it. You cannot. In that emptiness, the very question becomes meaningless. You may orient yourself any way you please, head toward one star, feet toward another, and nothing in the behavior of light, of motion, of any physical process whatsoever will inform you that you have chosen wrongly. The universe offers no compass, no preferred direction, no cosmic up, but perhaps you object. Surely gravity creates a real direction. Surely the pull you feel is evidence of something fundamental about space itself. Consider this thought experiment. Imagine you awake in a sealed chamber with no windows, no knowledge of where you are. You feel weight pressing you toward one wall. Can you determine whether you rest upon Earth's surface with gravity pulling you down, or whether you float in the void while the chamber accelerates in the opposite direction, pressing you against its floor? You cannot. No experiment you perform within that chamber will distinguish these cases. Drop a ball. It falls the same way in both situations. Swing a pendulum, it swings identically. The sensation you call gravity's direction cannot be separated from the effect of acceleration. What does this reveal? That what you call down is not a feature of space itself, but a response to circumstance, the circumstance of being near a massive body, or the circumstance of accelerating. Remove the circumstance, and the direction vanishes. The fish knows water so intimately it cannot conceive of air, yet air exists. You know down so intimately you cannot conceive of its absence. Yet in the vast emptiness between stars, which constitutes almost all of the cosmos, down does not exist. Here is the matter stated plainly. Every direction you experience as absolute is actually defined by your position relative to nearby massive bodies. The plumb line does not point toward some cosmic foundation. It points toward Earth's center. Move to the moon, and it points toward the moon's center. Move to empty space, and it points nowhere at all. Notice how this truth hides in plain sight. You observe that level surfaces on Earth are not flat but curved to follow the planet's shape, because level means perpendicular to down. which means perpendicular to the direction toward Earth's center. You observe that the plumb line hangs differently at different latitudes. You observe that water settles into spherical drops when briefly freed from gravitational constraint, because in that moment it has no preferred direction to follow. Every tool that finds down is actually finding the nearest massive body, nothing more. The error most make is assuming that because the sensation of down is so vivid, so constant, so inescapable, it must reflect something fundamental about space itself. But vividness proves only that you have never escaped your local circumstance. Not that escape is impossible. The prisoner who has never left his cell might believe the walls are the boundaries of the world. He would be wrong. And now your comfortable certainty begins to crumble. If down is merely local, merely the direction toward whatever mass happens to be nearby, then what else that you take for fundamental might be equally contingent. What other features of your experience have you mistaken for features of reality itself? The question presses forward. If spatial direction is not what you thought, what about temporal direction? You remember yesterday but not tomorrow. Causes precede effects. Time flows forward with the same apparent inevitability that objects fall down. Surely this arrow of time is fundamental. But here too, as we shall see, appearances deceive in ways even more profound. Time flows forward. This is not merely something you believe. It is something you live every moment of every day. You remember breakfast, but not dinner. You see the arrow leave the bow before it strikes the target. The wine spills from the cup. Never does spilled wine leap back into the vessel. Yesterday is fixed and done. Tomorrow remains uncertain. The arrow of time seems so fundamental to existence that imagining its reversal borders on madness. To suggest that time might not truly flow, that the past to future direction might be as much an illusion as the down we just examined, sounds like the fantasy of a philosopher who has lost his grip on reality. And yet, when we examine the equations that govern all motion, attending to their mathematical structure rather than to our assumptions about how nature must behave, we find something remarkable. These equations work identically whether time runs forward or backward. Consider what this means. Replace the symbol for time with its negative, reversing its direction, and the laws of motion remain valid. The mathematics makes no distinction between past and future. The equations that describe a ball rising into the air describe equally well a ball falling, the same motion, merely reversed. This is not a trick of mathematics. It reflects something deep about the laws governing all motion. To see this clearly, consider two billiard balls colliding upon a table. One strikes the other, they rebound. Each rolls away on its new path. Now imagine you have captured this collision on some recording device and can play it backward. In the reversed sequence, the balls approach from their final positions, collide, and roll away on their original paths. Does this reversed motion violate any principle of mechanics? Examine carefully. The balls approach, contact, rebound, all according to the same laws that govern the forward motion. Nothing in the reversed sequence is impossible. Nothing violates any principle of natural philosophy. The laws of motion are satisfied whether time runs forward or back. But now consider a different scene. An egg falling from a table and breaking upon the floor. Shell shatters, white and yolk spread across the stone. Play this backward, and the shards leap up, reassemble into a perfect shell. The contents collect themselves inside, and the intact egg rises smoothly to the tabletop. This never happens. We all know it never happens. The reversed motion seems absurd, impossible, a violation of everything we understand about how the world works. Yet here is the astonishing truth. Every interaction in that backward-running sequence satisfies the same mechanical laws as the forward sequence. Each fragment moving upward, each particle of white collecting back together, every individual motion obeys the equations perfectly. What forbids the egg from reassembling is not law, but something else entirely. Think carefully. For the egg to reassemble, billions upon billions of particles would need to move in precisely coordinated ways, each fragment traveling at exactly the right speed, in exactly the right direction, to meet its neighbors at exactly the right moment. The probability of this coordination arising by chance is not merely small. It is so fantastically small as to never occur in the lifetime of the universe. The egg stays broken, not because physics forbids reassembly, but because probability overwhelmingly prevents it. Whence it follows that what we call time's direction is not inscribed in the laws of motion themselves. It emerges from something else, from the overwhelming improbability of certain configurations, from what we might call the statistical arrangement of matter. And this arrangement traces back to a remarkable fact. The universe began in a highly ordered state. Physical processes move from order toward disorder, not because the laws command this, but because disordered arrangements are vastly more numerous than ordered ones. A shuffled deck is more likely than a sorted one, not because shuffling obeys different laws than sorting, but because there are so many more ways for cards to be out of order than in order. The arrow of time is the arrow of increasing disorder, and this arrow exists because of how things began, not because of how the laws are structured. To make this vivid, imagine filming the motions of the planets through a telescope, the great clockwork of the heavens turning through its cycles. Now play the recording backward. The planets orbit in the opposite sense. Moons circle contrary to before. Comets sweep through in reversed arcs. Does this reversed celestial motion violate any gravitational principle? It does not. Every orbit, every swing, every gravitational interaction satisfies the same equations running backward as forward. If someone showed you such a recording without telling you which way it truly ran, you could not determine from the physics alone whether you watched the original or the reversal. In the realm of pure mechanics, the direction of time is invisible. You experience time's direction so vividly because you are embedded in it. You remember the past because memory formation is itself a process that increases disorder. The act of recording an experience creates more ways for things to be arranged. You see causes precede effects because cause and effect are concepts you define by the direction in which disorder increases. But confusing your experience of time with time's fundamental nature is precisely the error we are exposing. Your experience emerges from the particular arrangement of matter in our region of cosmic history, not from any asymmetry in the laws themselves. Notice what has happened. We began by exposing the illusion of spatial direction, the false certainty that down is a cosmic truth rather than a local accident. Now we find temporal direction, the flow from past to future, resting on similarly contingent foundations. The laws are symmetric in time. The asymmetry emerges from initial conditions. The world you inhabit is not the world that is. Your most basic orientations in space and in time are painted scenery, local and contingent, mistaken for the bedrock of reality. The old certainties have crumbled, but what remains when we strip away these illusions? If directions are local and time's arrow is statistical, what principles do govern the cosmos? Here is where the investigation takes its most remarkable turn. For when we examine the equations without prejudice, attending to their mathematical structure, we discover they possess a property so profound that all of natural philosophy depends upon it. That property is symmetry. What does the universe actually look like when we examine its laws without the distortions of local circumstance? We have stripped away the illusion of absolute direction. We have exposed time's arrow as an emergent phenomenon rather than a fundamental feature. Now, we must construct true understanding in place of false certainty. Here is what we find when we attend to the mathematics governing all motion. The equations possess a remarkable property. Certain transformations can be applied to them without changing them. This is not poetic metaphor. It is precise mathematical fact. Let me show you what this means. Construct in your mind a chamber that can be rotated to any orientation in space. Within it, perform whatever experiments you please. Drop weights and observe their fall. Swing pendula and measure their periods. Pass light through prisms and observe how the colours separate. Record your results with care. Now rotate the chamber. Turn it 30 degrees, 60 degrees. Invert it entirely so that what was floor becomes ceiling. Perform the same experiments again. The results are unchanged. This is not merely an observation about your particular chamber. It is a property of the equations themselves, holding everywhere in the cosmos. The laws of motion do not care which direction you call north. They do not prefer up over down, left over right, this orientation over that. Rotate your coordinate system by any angle whatsoever, and the equations remain identical. This is rotational symmetry, and it is merely the beginning. Move your laboratory, relocate it 100 miles to the east, 1,000 miles to the south. Transport it in imagination to the remotest regions of the stellar realm, to planets circling distant stars, to the great void between the galaxies themselves. Perform your experiments again. The laws remain unchanged. This is translational symmetry. Space itself is uniform. No location is privileged. No place is special. The physics operating here operates identically there, everywhere, throughout the cosmos, without exception. Now consider yet another transformation. Imagine a vast mirror at the edge of reality, reflecting the entire universe. In that reflected cosmos, left and right are exchanged throughout. Every planet, every star, every particle reversed as if seen in a looking glass. In that mirror universe, do the laws of mechanics still hold? They do. What your left hand does, its reflection does equally well according to identical principles. The equations harbour no preference for one-handedness over the other. This is mirror symmetry. And finally, most remarkably, consider time itself. We have already seen that the equations governing motion work identically whether time runs forward or backward. Replace the symbol for time with its negative, and the laws remain valid. This is temporal symmetry. Now grasp what we have discovered. The fundamental equations that govern all motion, all force, all change in the natural world make no distinction between any direction in space versus any other, any location in space versus any other, left versus right, forward in time versus backward. Nature, at its deepest mathematical level, is profoundly indifferent. But what does this indifference mean? It is not merely a curious property of the mathematics. It is the foundation upon which all of natural philosophy rests. Consider, if the laws differed from place to place, knowledge gained here would not apply there. If the laws changed from moment to moment, principles established today would predict nothing about tomorrow. If the equations preferred one direction over another, the universe would be fundamentally unlike itself in different orientations. The uniformity of law across space is what makes it possible to understand distant stars. The uniformity across time is what makes prediction possible. The uniformity across direction is what allows the same principles to govern falling apples and orbiting moons. Symmetry is not decoration. It is the condition that makes physics possible at all. Hold a prism to sunlight and observe the spectrum of colours that emerges. Now rotate the prism, point it up, point it down, tilt it at any angle. The light separates into the same colours in the same order by the same principles. You are witnessing rotational symmetry in action. The behaviour of light makes no reference to which way up might be. Or watch a master clockmaker's mechanism, gears meshing, pendulums swinging, hands advancing around the dial. The clock works regardless of its orientation. Turn it on its side, hang it upside down. The principles governing its operation care nothing for direction. So, it is with the clockwork of the cosmos itself. The error most make is accepting that their experience is local while still imagining the universe must have some preferred directions, some distinguished orientations written into its deepest structure, some cosmic up that exists even if we cannot access it from our parochial position. But the equations themselves cannot distinguish what nothing marks as different. How could space prefer here over there when there is no feature to tell them apart? How could the laws favour one direction when all directions in empty space are identical? The very uniformity of space makes preference impossible. And this is where the inquiry takes its most remarkable turn. For we now discover that from this indifference, from these symmetries, consequences flow that explain the most fundamental principles of natural philosophy. The conservation laws themselves, those bedrock principles that seem to stand as independent axioms, are actually necessary consequences of symmetry. Why is momentum conserved? Why does energy persist through all transformations? These are not separate mysteries requiring separate explanations. They follow, with mathematical inevitability, from the symmetries we have just established. This is what we must now examine. Here is where most inquiries stop too soon. We have established that the laws of motion are symmetric, unchanged by rotation, by translation, by reflection, by temporal reversal. Many who reach this point nod in appreciation and move on, treating symmetry as an elegant curiosity, a pleasing property of the mathematics, but nothing more. They miss everything. For from these symmetries, consequences flow that transform our understanding of why nature behaves as it does. The conservation laws, those principles so fundamental, they seem to require no explanation, are actually derived truths flowing with mathematical necessity from the symmetries themselves. Begin with momentum. You observe that when objects collide, their individual motions may change dramatically, one ball speeding up, another slowing down, directions reversing, velocities exchanging. Yet if you calculate the total momentum before the collision and after, you find them equal. What was possessed in some before remains possessed in some after. This is the conservation of momentum. It holds without exception for any isolated system. It governs the recoil of cannon, the flight of birds, the collision of ships at sea, the motions of planets and moons. It is one of the foundational principles upon which all of natural philosophy rests. But why? The error most make is treating conservation as a brute fact, something observed countless times, verified beyond doubt, but accepted as foundational without asking what makes it so, as if nature simply chose this rule from among many possibilities. But nature did not choose. The conservation of momentum is not an arbitrary axiom. It is a mathematical consequence of a symmetry we have already established, the uniformity of space. Let me show you how. Imagine two balls colliding on a vast, featureless plane extending equally in all directions. Before the collision, each carries a certain momentum, mass times velocity. After, their individual momenta have changed, but the total remains unchanged. Why must this be so? Because the plane offers no preferred location. If the collision occurred 100 yards to the east, nothing about the physics would differ. 1,000 yards to the north, identical. The laws governing the collision make no reference to position, because position does not matter. Space is uniform. Now, here is the mathematical truth. When the laws of motion possess translational symmetry, when they do not change as you move from place to place, then there must exist a quantity that remains constant. The mathematics demands it. The symmetry guarantees it. That quantity is momentum. This is not interpretation. It is not philosophy. It is mathematical theorem. The connection between spatial uniformity and momentum conservation follows with the same certainty as geometric proofs, whence it follows that every time you observe momentum conserved in collision, in explosion, in any interaction whatsoever, you are witnessing the uniformity of space made manifest. The cannon recoils because the ball flies forward, and total momentum was zero before firing and must remain zero after. This is not some mysterious principle imposed from outside. It is space's indifference to location, guaranteeing that what was possessed in some must remain possessed in some. You thought conservation laws were fundamental and symmetries were interesting properties. The truth is precisely backward. Symmetry is fundamental. Conservation follows. Consider the implications. We do not accept momentum conservation as an axiom requiring no further explanation. We derive it from something deeper, from the uniformity of space itself. And this derivation tells us something profound. Momentum conservation is not a contingent fact that might have been otherwise. It is a necessary consequence of space being what space is. Could momentum fail to be conserved? Only if space were not uniform, if the laws governing motion differed from place to place. But in uniform space, where no location is privileged above any other, conservation follows with mathematical inevitability. This inverts the hierarchy of explanation you likely held before. You thought conservation was bedrock. Now you see it resting on something deeper still. Symmetry. And symmetry itself rests on the uniformity of space, which seems almost logically necessary. For how could featureless void prefer one location over another? Watch now with new eyes when you see objects collide, the billiard balls exchanging velocities, the ships meeting at sea, the ice skaters pushing off from one another and gliding in opposite directions. You are not observing some arbitrary rule that nature happens to follow. You are witnessing the uniformity of space, that profound indifference to location, expressing itself through the mathematics of motion. The same laws operate here as there. This sameness guarantees that something is preserved, that something is momentum. And now the question naturally arises, if spatial uniformity guarantees momentum conservation, what does temporal uniformity guarantee? If the law's indifference to where preserves momentum, what does their indifference to when preserve? The answer awaits. The pendulum swings in your chamber. It swung the same way yesterday. It will swing the same way tomorrow. A century hence, if the mechanism endures, it will swing by the same principles it obeys today. The laws governing its motion do not change with time. This temporal uniformity, this constancy of physical law across the ages, is another symmetry, perhaps the most remarkable of all. And from it, another conservation law follows with the same mathematical inevitability we have just witnessed. That law is the conservation of energy. You observe this conservation everywhere, though you may not have recognized its source. A ball rolls uphill and slows. It reverses and speeds as it descends. The motion has transformed into height. The height transforms back into motion. Through all these transformations, something remains constant. We call it energy. The pendulum trades height for speed at the bottom of its arc, speed for height at the top. Back and forth, cycle after cycle, the total energy, motion plus position, remains unchanged. This is not because some external rule commands it. It is because the laws governing the pendulum today are identical to the laws that governed it yesterday and will govern it tomorrow. Here is the mathematical truth. When the laws of motion do not change with time, there must exist a conserved quantity. The temporal symmetry guarantees it. That quantity is energy. Consider what this means. A machine that produces more energy than it consumes would require the laws of physics to favor the future over the past in some way, to treat tomorrow differently from today. But temporal symmetry forbids precisely this. The laws make no distinction between moments. They are the same at every instant. Whence it follows that energy cannot be created from nothing. It cannot vanish into nothing. It can only transform from motion to heat to height to light. But the total persists through all transformations. This is why perpetual motion machines are impossible. Not because of some arbitrary prohibition, but because their operation would require time to be non-uniform, for the laws of nature to differ between one moment and the next. In a universe where tomorrow's physics equals today's, energy must be conserved. And by the same reasoning, rotational symmetry, the indifference of the laws to orientation, guarantees the conservation of angular momentum. Because no direction in space is privileged, spinning bodies must maintain their rotation unless external forces intervene. The skater draws in her arms and spins faster. She extends them and slows. The total angular momentum remains constant because space harbours no preferred orientation to disturb it. See now the architecture that has emerged. Momentum is conserved because space is uniform in location. Energy is conserved because time is uniform across moments. Angular momentum is conserved because space is uniform in direction. These three great conservation principles, pillars upon which all of mechanics rests, are not independent axioms requiring separate justification. They flow from a single source, the symmetries of space and time. The scattered pieces reveal their pattern. What seemed like three separate mysteries dissolves into one unified understanding. Symmetry is the foundation. Conservation is the consequence. Watch the ball rolling uphill, slowing, stopping, reversing, speeding down. You witness temporal symmetry made visible, the same laws operating at each moment, guaranteeing that the energy present at the start remains present at the end. Watch colliding objects exchange their velocities while preserving their total momentum. You witness spatial symmetry in action, the same laws at each location, guaranteeing that what was possessed in some stays possessed in some. Watch the spinning top maintain its rotation, the gyroscope resist displacement, the planet hold its orbit. You witness rotational symmetry expressing itself, no direction privileged, no orientation preferred, angular momentum preserved. The elegance of this arrangement cannot be overstated. Nature did not postulate three separate conservation laws for three separate quantities. Nature possesses symmetric laws, and the conservation laws follow, all of them, necessarily, from the uniformity of space and time. But here the deepest tension emerges. We have established that the laws are symmetric in time, that the equations work identically forward and backward. We have shown that spatial uniformity explains momentum conservation and temporal uniformity explains energy conservation. Yet you still experience time flowing forward. Tea still cools but never heats. Eggs still break but never reassemble. Trees still grow upward. Rivers still flow to the sea. If the laws are symmetric, why is the world so manifestly asymmetric? We have exposed the illusion, established the true architecture, and shown what follows from it. But we have not yet reconciled the symmetric laws with the asymmetric phenomena. We have not explained how a universe governed by indifferent equations produces the directed experience you inhabit every moment of every day. This reconciliation is what we must now achieve. We have arrived at the heart of the apparent paradox. The laws governing all motion are symmetric. They make no distinction between directions in space, between locations, between forward and backward in time. We have established this with mathematical certainty, and from these symmetries flow the conservation principles that undergird all of natural philosophy. Yet look around you. Trees grow upward, never downward. Rivers flow to the sea, never from it. Heat passes from fire to cold hands, never the reverse. Time carries you relentlessly from yesterday toward tomorrow, never returning you to the past. The world you inhabit is manifestly, obviously, inescapably asymmetric. How can both truths hold? How can symmetric laws produce an asymmetric world? Here is the resolution, and it transforms everything. The laws tell you what is possible. They tell you how possibilities evolve, but they do not tell you which possibilities are realized. That is determined by something else entirely, the circumstances in which the laws operate. Consider a ball resting on a perfectly level surface. According to the laws of motion, the ball may roll left or it may roll right. The equations make no distinction. The symmetry between left and right is preserved in the laws themselves. But now, tilt the surface. Introduce a gradient, one side higher than the other. The ball rolls toward the lower end. It rolls in one direction rather than the other, not because the laws prefer that direction, but because the circumstance, the tilt, has broken the symmetry. The laws themselves remain symmetric. They still make no inherent distinction between left and right, but the circumstance does, and symmetric laws acting upon asymmetric circumstances produce asymmetric outcomes. This is the key that unlocks everything. Consider the tree growing upward. Does the tree grow in that direction because up is written into the laws of nature? Does some fundamental principle prefer vertical growth toward the sky? It does not. The tree grows upward because gravity creates a gradient pointing toward Earth's center, and the tree has developed in that gravitational environment. The chemistry governing growth makes no inherent distinction between up and down, but the circumstance does. Place a seedling in a chamber far from any massive body, free of gravitational gradient, and it would grow haphazardly, sending shoots in any direction. The asymmetric growth reflects the asymmetric environment. The laws remain symmetric. The circumstances break the symmetry. Now consider the deepest asymmetry of all, the direction of time. We have established that the equations of motion work identically whether time runs forward or backward. Yet eggs break and never reassemble. Tea cools and never spontaneously heats. You remember yesterday and not tomorrow. How does this temporal asymmetry emerge from time's symmetric laws? The answer lies in how the universe began. The early cosmos existed in a state of remarkable order, a highly organized arrangement of matter and energy. Physical processes, governed by time's symmetric laws, move from this ordered beginning toward disorder. Not because the laws command this direction, but because disordered arrangements are overwhelmingly more numerous than ordered ones. Think of a deck of cards arranged in perfect sequence, hearts in order, then diamonds, then clubs, then spades. Shuffle the deck randomly. What arrangement do you get? Almost certainly a disordered one. Not because the laws of shuffling prefer disorder, but because there are vastly more disordered arrangements than ordered ones. The universe began, so to speak, as a sorted deck. Physical processes shuffle it, and shuffling almost always moves toward disorder simply because disorder is overwhelmingly more probable. This is why eggs break but never reassemble. The reassembly would require shuffling toward a more ordered state, moving against the overwhelming tide of probability. The laws permit it. Probability forbids it. The arrow of time is not inscribed in the laws. It emerges from the accident of initial conditions, from the remarkable fact that the universe began highly ordered, providing a direction for disorder to increase. Whence it follows that every asymmetry you observe in the natural world is not a feature of the laws themselves, but a consequence of circumstances breaking the symmetry that the laws preserve. The river flows to the sea because the terrain creates a gradient, high ground here, low ground there. The fire consumes the wood because the chemical arrangement moves toward states of greater probability. Heat flows from hot to cold because molecular motion spreads from regions of concentration. In every case, the underlying laws are symmetric. In every case, asymmetric circumstances select which of the many possibilities permitted by those laws actually manifests. Perform this observation. Find a ball and a level surface. Place the ball at rest. It remains motionless because no circumstance breaks the symmetry between rolling left or rolling right. Now tilt the surface ever so slightly. The ball moves. You have not changed the laws governing its motion. You have introduced a circumstance that breaks the symmetry. Every rolling ball, every flowing river, every growing tree, every cooling cup exemplifies this same principle. Symmetric laws plus asymmetric conditions yield asymmetric outcomes. The rules of chess make no inherent distinction between the white player and the black. The rules are symmetric, yet any actual game develops asymmetrically. One player attacks, the other defends. One gains advantage, the other struggles. The asymmetry arises not from the rules, but from the sequence of moves, the particular history of that game. So it is with the cosmos. The laws are symmetric. The particular history, the specific initial conditions, the way matter was arranged at the beginning, introduces all the asymmetry we observe. And this reveals something profound about the universe we inhabit. Since the asymmetries emerge from initial conditions rather than necessary law, the universe could have begun differently. The arrow of time could point otherwise in other regions of existence. The particular arrangement of matter that gives us up and down, past and future, order and disorder. This is one history among countless others that the symmetric laws would permit. We do not merely live in a universe, we live in this particular version of what the laws allow. One garden among infinitely many that might have bloomed from the same symmetric soil. The apparent contradiction dissolves. Symmetric laws and asymmetric experience are not at war. They are complementary levels of description, the laws providing the possibilities, the circumstances selecting which possibilities flower into actuality. But this reconciliation carries implications far beyond physics. It transforms how we understand explanation itself, how we reason about cause and consequence in every domain. And it reveals why knowledge of distant stars and ancient times is possible at all. Stand outside on a clear night and look upward at the stars. Those points of light are suns, some larger than our own, some smaller, all vastly distant. The light reaching your eyes tonight left those stars years ago, decades ago, centuries ago. You observe not what those stars are now, but what they were when the light began its journey. Here is a question that might seem unanswerable. How can we know anything about those distant fires? We cannot travel to them. We cannot experiment upon them. We receive only the faint light that crosses the void. Yet we do know. We know what elements burn in their hearts. We know the principles governing their motion. We can predict where they will be a century hence with remarkable precision. How is this possible? It is possible because the laws of nature are the same there as here. The light separating through a prism in your chamber follows the same principles as light from the remotest star. The gravitational attraction holding the moon in orbit operates by the same rules as the attraction governing stars orbiting the center of a distant galaxy. The laws deduced here apply there, everywhere, throughout the cosmos, without exception. This is the gift of translational symmetry. Because the equations do not depend on location, physics discovered on Earth applies universally. We do not merely hope this is true. It follows necessarily from the mathematical structure of the laws themselves. Consider the comet that sweeps through the heavens, appearing periodically across the centuries. Ancient astronomers recorded its passage. We predict its return. The prediction succeeds because the gravitational principles operating today operated when the ancients watched the skies and will operate when our descendants scan the heavens. This is the gift of temporal symmetry. Because the equations do not change with time, physics established in one era applies to all eras. The laws that govern motion this morning governed it 1,000 years past and will govern it 1,000 years hence. Without these symmetries, natural philosophy would be impossible. Imagine for a moment a universe where the laws differed from place to place, where gravity pulled differently here than there, where light behaved one way on Earth and another way among the stars. In such a universe, knowledge gained in your chamber would apply nowhere else. Prediction would fail. Every location would require its own physics, discovered anew from local observation. Understanding would fragment into a chaos of local descriptions with no universal pattern. Or imagine a universe where the laws changed with time, where today's physics bore no relation to yesterday's, where tomorrow would bring principles entirely different from those we know. In such a universe, the past would teach nothing about the future. Experiment would be pointless, since today's results would not apply tomorrow. The comet's return could not be predicted because the rules governing its motion might differ entirely by the time it arrived. The symmetries we have established are what rescue natural philosophy from such chaos. Because space is uniform, what we learn here applies everywhere. The gravitational attraction measured on Earth, the same attraction that governs the falling apple, governs the orbiting moon, the circling planets, the wheeling galaxies, the motion of everything everywhere. That one principle should unite the falling fruit and the celestial spheres. This unity is not a happy accident. It is guaranteed by the uniformity of space. Because time is uniform, what we establish now remains valid always. The laws that governed motion in ancient times, when the pyramids rose and the philosophers debated in Athens, are the same laws that govern motion today and will govern it when all our works have crumbled to dust. This permanence is not mere observation. It is necessitated by the structure of the mathematics. You observe the tides rising and falling, responding to the moon's pull across 250,000 miles of void. You observe the same gravitational attraction that makes the apple fall, making the seas rise. You observe comets returning on schedules predicted centuries in advance, their motions governed by laws deduced from observations made in entirely different centuries. This is symmetry made practical. This is the uniformity of space and time transformed into the possibility of knowledge. Notice how the optical principles explaining the rainbow, the separation of sunlight into colours by water droplets in the air, are the same principles governing light from the most distant stars. The spectrum of stellar light, analysed through prism and instrument, reveals the elements burning in those far-off furnaces. We know the composition of stars we will never visit because the behaviour of light is the same everywhere. Notice how the gravitational principles governing projectiles thrown upon Earth, the curve of the cannonball, the arc of the fountain's water, are identical to those governing planets in their orbits. The same mathematics describes both. This is not analogy or metaphor. It is identity. One law, one principle, governing all motion everywhere. The ancient longing to unify heaven and earth, to find common principles governing both the terrestrial and the celestial, finds its fulfillment here. Not through philosophical speculation, but through demonstrated mathematics. The same equations, the same symmetries, the same conservation laws, operating from the smallest pebble to the most massive star. This is the achievement of natural philosophy, not merely to describe local phenomena, but to establish universal principles. And this universality is possible only because of symmetry, because space does not prefer here over there, because time does not favour now over then, because the laws are indifferent to location and moment. The cosmos becomes comprehensible, one system governed by one set of principles, knowable because those principles do not change from place to place or time to time. We have journeyed from illusion through principle to reconciliation. We have exposed the false certainties of directional space and flowing time. We have established the symmetric architecture of physical law. We have shown how asymmetric phenomena emerge from symmetric laws meeting asymmetric circumstances. And we have seen how symmetry makes universal knowledge possible. What remains is to embody this understanding, to transform it from something known to something seen, to perceive the symmetric foundation beneath every asymmetric appearance, in every phenomenon we encounter for the rest of our days. This is the final transformation. You now possess a tool that will serve you as long as you live. It is a single question, applicable to any physical phenomenon you encounter, a diagnostic that reveals hidden structure, exposes false assumptions, and leads unfailingly toward deeper understanding. The question is this: what circumstance broke the symmetry that the laws preserve? When you see any asymmetric phenomenon, any process that goes one way rather than another, any outcome that favours one direction over its opposite, you know that the laws themselves harbour no such preference. The asymmetry must come from circumstances. Your task is to identify them. Let me show you how this works. Your tea sits on the table, steaming. Over time, it cools to room temperature. The reverse, room temperature tea spontaneously heating while the air around it cools, never occurs. Here is an asymmetry. Heat flows in one direction, but not the other. Ask the question, what circumstance broke the symmetry? The circumstance is the temperature difference itself. The tea began hot, the air began cool. This initial arrangement is asymmetric. The laws governing molecular motion make no inherent distinction between hot to cold and cold to hot, but given this particular starting arrangement, the overwhelming probability is motion toward equilibrium. The cooling is not commanded by law. It is selected by probability, acting upon asymmetric initial conditions. Now consider smoke rising from a flame. Here is another asymmetry. The smoke goes up, not down. The laws of motion do not prefer upward motion. We have established this. What circumstance breaks the symmetry? The circumstance is Earth's gravitational gradient combined with the smoke's lower density than surrounding air. Remove the gravitational gradient, imagine the flame burning in the void between stars, and the smoke would expand in all directions equally. The rising is not written into physics, it is written into the environment. Consider the river flowing to the sea. The laws governing fluid motion make no distinction between flowing toward the ocean and flowing away from it. What circumstance breaks the symmetry? The circumstance is the elevation gradient created by Earth's surface. Water flows downhill because downhill exists, because the terrain provides a gradient from high potential to low. On a perfectly spherical, featureless Earth with no elevation differences, water would not flow at all. Now consider the deepest example, your memory of the past, but not the future. This seems unlike the others, a fundamental feature of consciousness rather than physics. But the question applies here too. Memory formation is a physical process. Encoding an experience, whether in the patterns of your mind or the scratches of a quill upon paper, increases disorder overall, even as it creates local order. The act of recording is itself governed by the arrow of disorder. What circumstance breaks the symmetry? The same one that gives all of time its apparent direction. The low disorder beginning of the cosmos. You remember yesterday because memory formation proceeded in the direction of increasing disorder. You cannot remember tomorrow because that would require disorder to decrease, would require the overwhelming tide of probability to reverse. The question reveals that even consciousness, even memory, even the intimate sense of time flowing that defines your experience, all rest upon the same foundation we have been examining. Symmetric laws, asymmetric initial conditions, asymmetric outcomes. This reframes how you understand explanation itself. You once heard, "Why does the ball roll left?" and expected an answer invoking some property of leftward motion, some reason why left is preferred. Now you understand. The answer must identify what circumstance broke the symmetry. The ground tilts, a hand pushed, a breeze blows from the right. The law itself harbours no preference. The circumstance introduces all the direction. Apply this consistently, and your reasoning transforms. Why does heat flow from the fire to your hands? Not because hot to cold is written into law, but because the temperature difference, the circumstance, breaks the symmetry. Why do objects fall when released? Not because down is fundamental, but because Earth's mass creates the circumstance, the gravitational gradient, that breaks spatial symmetry locally. Why do eggs break but never reassemble? Not because physics forbids reassembly, but because the ordered initial state, the intact egg, is a circumstance from which almost all paths lead toward disorder. For one day, practice this. Whenever you observe a directional phenomenon, something going one way rather than another, Ask, what broke the symmetry? The falling raindrop. Gravity creates the gradient. The spreading ink drop in water. Diffusion moves toward more probable arrangements. The burning candle. Chemical energy finds its direction toward disorder. The clock running down. The wound spring provides the initial asymmetry. The laws merely describe how that asymmetry dissipates. By evening, you will see differently. Not just the phenomena, but the structure beneath them. Not just what happens, but why it happens in that direction rather than another. You will perceive circumstances where you once perceived necessities, contingencies where you once perceived fixed truths. The question opens every door because every door is the same door. Every asymmetric phenomenon has the same structure, symmetric laws, asymmetric circumstances, asymmetric outcomes. The particular circumstances differ. The pattern is universal. Much that seems necessary is actually contingent. The direction of time, the direction of heat flow, the direction of growth. These are not built into the fabric of reality. They are consequences of the particular cosmic history we inhabit. The laws permit countless other arrangements. Our circumstances select the ones we experience. This recognition breeds intellectual humility. The universe need not have been as it is. We live in one actualization of what the symmetric laws allow, one particular flowering among infinitely many possible gardens. But one question remains. We have seen what the symmetries are and what follows from them. We have learned to perceive them operating beneath every phenomenon. But we have not yet asked the deepest question of all. Why are the laws symmetric in the first place? Is this merely a fortunate accident? Or is there something deeper still? Some necessity that makes the symmetries inevitable? Here lies the final wonder. We stand now at the culmination of our inquiry. We have traced the journey from illusion to understanding, from false certainty about spatial and temporal direction to the recognition that these are local circumstances, not cosmic truths. We have established the symmetric architecture of physical law, the profound indifference of the equations to location, direction, orientation, and temporal order. We have derived the conservation principles from these symmetries, shown how asymmetric phenomena emerge from asymmetric circumstances, and learned to perceive the symmetric foundation beneath every observation. One question remains, the deepest question. The question that transforms understanding into wonder. Why must the laws be symmetric? We have accepted symmetry as a property of the equations. We have shown what follows from it. But is symmetry itself merely contingent, something the universe happens to have, but might have lacked? Or is there something that makes it necessary? Consider what asymmetric laws would require. For the laws of motion to prefer one location over another, to treat here differently from there, some feature would have to distinguish them, some marker, some property, some characteristic that makes this place different from that place. But empty space contains no such features. Between the stars, in the void where nothing exists, there is nothing to distinguish one location from another. No boundaries, no markers, no distinguishing characteristics. The void is featureless. How could featureless void prefer one location? It cannot. There is nothing to make the preference. The very uniformity that makes space what it is makes physical law symmetric with respect to location. The same reasoning applies to direction. For the laws to prefer up over down or left over right, some feature would have to distinguish these directions in empty space itself. But empty space is isotropic, the same in all directions. There is nothing to pick out one direction as special. Rotational symmetry follows not as a choice nature made, but as a consequence of what empty space is. And for time, for the laws to prefer forward over backward, some feature would have to mark the distinction in the temporal dimension itself. But the mathematical structure of time, like that of space, contains no such markers. The equations governing motion find nothing in time's fabric that distinguishes one direction from the other. The symmetries are not choices, they are necessities. They follow from the nature of space and time themselves, from the featureless uniformity of the arena in which all physics unfolds. Nature could not have built in preferences because there is nothing to prefer. The indifference of the laws is the only possibility. And from this necessity, everything else follows. Momentum must be conserved because spatial uniformity cannot be otherwise. Energy must be conserved because temporal uniformity cannot be otherwise. The conservation laws are not happy accidents or arbitrary rules. They are derived truths, flowing with mathematical certainty from symmetries that could not be otherwise, which themselves flow from the nature of space and time. The architecture of physics is more economical than it first appears. At the deepest level sit the symmetries, necessary features of uniform space and time. From these symmetries, by mathematical derivation, flow the conservation laws. From the conservation laws, combined with the specific forces and circumstances, flow all the phenomena we observe. The hierarchy of explanation runs from symmetry down to observation, not from observation up to arbitrary postulate. You thought conservation laws were fundamental. You learned they derived from symmetries. You now see that the symmetries themselves are necessary, the only way coherent physical law can operate in uniform space and time. Imagine a universe where space was not uniform, where the laws differed from place to place with no feature marking the differences. In such a universe, momentum would not be conserved. Prediction would fail. Knowledge gained here would not apply there. Physics would fragment into local descriptions, each valid only at its own location. Natural philosophy itself would be impossible. The symmetry we have discovered is not merely a pleasant feature of our universe. It is the precondition for understanding the cosmos at all. Without it, there could be no physics, no prediction, no accumulated knowledge of nature. The uniformity of law makes science possible. That the universe should operate by such principles, symmetric, economical, necessary, and that finite minds should be capable of grasping these principles. This is cause for wonder that does not diminish upon examination. Look now at the world around you, the falling stone, the swinging pendulum, the orbiting moon, the cooling tea, the growing tree, the flowing river, the passage of time itself. You see not merely phenomena, but the structure beneath phenomena. Symmetric laws guaranteeing conservation. Conservation constraining possibility. Circumstances selecting which possibilities manifest. And beneath it all, the necessary uniformity of space and time that makes the architecture possible. The elegance is not imposed from outside. It is revealed from within. The laws are elegant because they could not be otherwise. The conservation principles are necessary because symmetry is necessary. And symmetry is necessary because space and time, by their very nature, offer no features upon which preferences could be built. We began with the misconception that the world is fundamentally asymmetric, that up and down, past and future, left and right, are written into the fabric of reality. We end with the understanding that the fabric of reality is symmetric to its core. The asymmetries you perceive are not cracks in nature's uniformity, but flowers growing from it, the varied blossoms of particular circumstances meeting universal, indifferent, necessary law. There is grandeur in this view. Beneath the chaos and variety of the world, the endless diversity of phenomena, the apparent disorder of events, the seeming complexity of nature, perfect mathematical symmetry governs all. The laws make no distinctions because there are no distinctions to be made in uniform space and time. The conservation principles hold because symmetry necessitates them. And from this necessary foundation, through the accident of initial conditions, all the asymmetric richness of the cosmos unfolds. You thought you understood asymmetry. Now you understand that what you perceived as fundamental was contingent, the expression of particular circumstances through universal law. The tree grows upward because gravity creates the local gradient. The fire burns because disorder has a direction to increase. The river flows because elevation provides the slope. In every case, the law is symmetric. The asymmetry blooms from circumstance, and the symmetry itself is not optional. It is the necessary character of physics in uniform space and time. Without it, coherent law becomes impossible. With it, all else follows. The great ocean of truth lies before you, vast and largely unexplored. We have found a few pebbles smoothed by the waves, the symmetries, the conservation laws, the mechanism by which asymmetric experience emerges. But the ocean stretches infinite, and greater discoveries await those who learn to see as we have learned to see. You will never observe the falling stone, the cooling tea, the passage of time the same way again, not because you have learned new facts, though you have, but because you have learned to see the symmetric foundation beneath every asymmetric appearance, the necessary architecture beneath every contingent phenomenon, the uniform laws beneath the varied circumstances of our particular cosmic history. This is the transformation complete. Nature plays no favorites. The cosmos, at its deepest level, balances perfectly on the point of symmetry. And from that perfect balance, through the accident of how things began, all the richness and variety and apparent asymmetry of the world unfolds. The laws are elegant because they could not be otherwise, and we, who have evolved within this cosmos, have been granted minds capable of perceiving the elegance. This is perhaps the greatest wonder of all.